Okay, good morning, good evening, good afternoon, depending on where you are. Today is August 18th, if I didn't miss the date. Uh, and we have a single item in our agenda. It's about Q. Alda and Abdullah will be presenting a Q overview to fit into the series of presenting various um, batch frameworks that exist in the Kubernetes ecosystem. So take it away from here.
Can I have some moderator or co-presenter permissions?
Yeah, give me a sec. For me, Zoom is jumping between windows and is
Okay, I think I have it
I
now.
just,
yeah, I think
yeah,
I'll do.
I did it.
Yeah,
And let's see if it works today. Okay, can you see my screen?
support for high Q. Yes,
Okay, um, and let's hope the slideshow works. Yes?
yes, it works.
All right, perfect. So, hello everyone, my name is Aldo, and Abdullah is joining me to present Q. Um, so as you might know, Q is a project sponsored by Six Scheduling. Um, so here we're gonna go through the motivations of what led us to build this system and the APIs, and if there's time, we have a short demo for you. Um, so the problem, of course, this is why we are here. We are talking about job queuing. Uh, we have a limited set of resources in our clusters, and then we have multiple tenants sending jobs to the cluster. So we need to decide which jobs should wait and which can start at a given time. Um, why is it necessary to do job queuing? Well, again, we have too many jobs, limited resources. In particular, if we're talking about on-prem clusters, uh, these clusters are generally static, uh, so the resources are very limited. And in the cloud, theoretically, you could have infinite amount of capacity, but in reality, that's not true because you might have discounts for a specific size. You want to establish quotas between your tenants. And of course, the clusters cannot scale to infinity. Kubernetes has certain limitations. So we need job queuing even in the cloud. Um, so why we built Q? Why we didn't use whatever was existing already in the ecosystem? So first, what was wrong with plain Kubernetes? So in Kubernetes, in the if we consider the kube scheduler, the kube scheduler will continuously attempt to start pods. Uh, and if these pods have dependencies between each other, we can have pods that basically starve the cluster. And you could have pending pods. They start queuing up in memory queue of the scheduler. Everything starts to go slow. On the other hand, Kubernetes offers the concept of quotas, but quotas are enforced at resource creation. So if you could only say, I have this limit of resources for my pods, um, but I cannot enforce this quota at the job level, for example. And and once my pod failed to be created, there is no place where it's queued. I have to retry. And it's not possible to express order or priority for these pods to be accepted. So these are the two main problems in plain Kubernetes. Now, of course, there are existing custom schedulers that uh, try to also fight these problems. But the problems that we found with them is that first, a lot of them re-implemented a lot of existing functionality. So a lot of them replaced Kube Scheduler, for example. A lot of them replaced the job controller or introduce a new job API, um, which it makes it hard to maintain, it makes it harder for portability, etc. Um, More importantly, these schedulers didn't have a clear integration with autoscaling, with the cluster autoscaler, and as such, it's very hard to use these schedulers in the cloud. Um, and an additional problem, which came from customer um, research, is that customers want resource fungibility or flexibility. Uh, for example, in the cloud, you could have VMs on demand, or you could use spot VMs. Um, so a job might want to use spot VMs whenever they are available. But if we run out of spot VMs and the job is a high priority, we still want to be able to jump into another VM type or another resource model. If I'm talking about GPUs, I could opt into a slower GPU that is more available. So this kind of resource flexibility is also not available in existing schedulers that we found. So here is the proposal that Q is bringing. Q is an operator. So you can install it on top of your existing cluster, and it would play well with uh, the existing kernel of Kubernetes. The implementation is slim. It doesn't because it doesn't re-implement kube scheduler. It doesn't re-implement cluster autoscaler or the job controller. The implementation is rather small, uh, while still providing um, all the functionality needed for job queuing. Again, we obtend to reuse core Kubernetes as uh, the maximum amount of APIs and components we can reuse from core Kubernetes. And this leads to a full compatibility with the ecosystem. Um, so now I want to talk a little bit about the APIs, the resource model. So we decided to go with the namespace as the tenant abstraction. I mean, it's already a canonical tenant abstraction, so we started from there. And then there are two closely related resources. One is a queue, the other one is a cluster queue. A queue is a namespace object, and you can use it to group closely related jobs from a single tenant. Um, and then we have a cluster queue, which is actually what governs the pool of resources. So in the cluster queue, you can define, you can see here the quota. Um, this is a simplified view of the API, but you can say how many cores you want. You can have by minimum, or you can spill over to 200. And then it defines some boundaries for fair sharing. So here you can see this field called cohort. We're going to see a little bit more about it in a bit. So, and here we are highlighting existing resources. So the job is the Kubernetes job API. Uh, Now, if we have multiple namespaces, each namespace has its queue. Uh, researchers send jobs to their queue, and then the queue sends the jobs to the cluster queue. And here is where the fair sharing happens. Um, and you could have more complex scenarios. So this is where the cohort comes in place. Um, you have so the idea is that if this cluster queue is not using all of its resources, then the robotics pool cluster queue can spill over and use the quota the quota that this cluster NLP pool is not using. And then you can still have cluster queues that don't borrow to others because they might be more expensive or whatever your motivations are. Um, if I can stop here if there are any questions so far. Otherwise, I'll go into more details in the API.
I have a couple questions.
Mm,
Can you hear
okay.
me?
So we
Hold
we
on,
have
hold on. Diana had
yes.
questions. Go
Okay,
ahead,
yes,
Diana.
I'm looking at the screen, so you have to talk to me.
Oh,
Yeah, sure.
sorry, I did. I'm not, can you hear me?
Yes.
Unclear.
Okay, great. So just a couple questions.
Mhm.
When you were talking about the some of the motivations where the scheduler, there's a lot of the scheduler could get overwhelmed with a lot of requests that just aren't satisfiable because of the limitation of the resources. Um, and, and you don't have to answer this now, but have you compared the overall performance with and without Q with regards to the scenario when you overload the control plane, basically, uh, and how the control plane benefits from having the queuing system? Have you done any experiments with that? And you can answer
Yes.
that later.
Right. So we haven't. We are on the works to build our scalability tests. Um, but the big benefit of Q, why the reason why Q wouldn't cause these kind of problems is because Q restricts the pod
Okay.
creation.
Yeah.
So the scheduler itself doesn't have pods to process before Q has the chance to allow these jobs to proceed.
Yeah, that's great. Yeah, and I'm interested in knowing how this the I guess the testing with regards to the enablement of Q. Now you've reduced the overhead on the control plane, which I think will show a lot of value of being able to have this queuing system and reducing the overhead. So yeah, that was one thing. And then the other question I had, um, when you talked a little bit about borrowing from the quota, uh, is this borrowing also enabling preemption as well? In other words, there was borrowing, but then the associated queue wants to have some of its resources back, or is it once you borrow, then you have to wait for the release of resources?
Yes, for now we are relying on the jobs to finish
Okay,
to recover the quota, but preemption is in our roadmap for the end of this year.
awesome. Thank you.
Let me, so if there are no more questions, I would like to go through here before I go through the APIs. Um, and then what Diana asked might become more clear. So this is how the operation of queue happens. So first we have the batch administrator, the administrator of the cluster. This persona creates the namespaces, creates the queues, creates the cluster queues uh, to set up the quotas and the fair sharing, etc. Now the batch user, or like for example the researcher, the only thing they need to do is they have to create a V1 job, and they set the queue name. Um, Now then queue comes into play based on the quota and the order, priorities, etc. It would admit the job, and during admission, it would inject node affinities. This is where the resource fungibility happens. The node affinities, for example, for spot VMs or a particular GPU model, will get injected into the job, and then the job is unsuspended. Then the job controller would observe that the job is unsuspended, and then it will start creating the pods, and then the kube scheduler would schedule the pods. So yeah, this is what we mean by Slim implementation. This job controller, this queue controller is acting in this pipeline, and then the rest of the system works as intended. Um, so with that, I think I can get back to the APIs.
So I have a question then.
Yes.
So in that operations, like every job that you submit should have the capability to suspend itself.
Right. Yes. We already did that for the V1 job. Um, but if you want to add support for a custom job, it just has to have the semantics of suspension. I can go over that in a bit as well. So back to the job, pretty much nothing changes. You just add an annotation with the queue name. Internally, Q would create a separate entity for this, which has the queue name and other things. The Q API, it's a namespace object, so it lives in your namespace, and it points to a cluster queue. In the future, we might want to add some more fields so that uh, you can control quota even for yourself as a researcher. Um, it might come handy. And then the most important object is the cluster queue. This is where most of the things are defined. Um, so we already talked about the cohort. So this is where we define which other which other cluster queues can drain or use resources from this one. And then you define which resources this cluster queue is governing. So for example, for CPU, we have defined a couple of flavors. Uh, so the flavor on demand and the flavor spot. Now, these for a flavor, you can define labels, right? So these labels are going to be injected. So Q will observe the quota. If there is quota for on demand, it will insert the labels for on demand, and then your workloads, your pods will, since they already have the affinity, they would start on these particular nodes. If there is no quota, then it will go to the next flavor, and it would assign these labels. Now you can also define taints. So if this flavor is I don't know, it has certain requirements, then you can define your pod can set up toleration for this flavor. Um, these uh, these two um, these two values, we had a hard time naming them. We call them max for now, but min means that this is kind of like your guaranteed capacity. This is the capacity that your cluster queue really has. And then max is the capacity that can be borrowed from the rest of the cohort. Um, so this is how you define um, how much you can borrow. Uh, well, I already explained through this. Uh, and that's it. With that, any questions here?
I had another question. I'm not sure I understand. So it's this part where in the injection of the node affinity, that
Mhm.
is it, is that, can you help me understand a little bit more? Is it the request is checked against the associated quota? And then once it passes, or it's allowed to allocate some of those quotas, how does the node affinity change the way the job gets dispatched or released?
So the node affinity gets inserted into the pod spec template
Okay,
of the job,
okay,
so that every pod that is created has this affinity. And then they will go into this particular, the nodes that have these labels.
I see. I got it. Okay.
Mhm.
Okay, and that's how essentially it's released.
Yes, at the same time we release the job, we unsuspend the job, we insert the affinities.
Okay, got it.
Mhm.
Thank you.
So
Uh,
what do we
Sorry, can you,
expect? Oh yeah,
sorry,
yeah.
Aldo, question. Can you explain to me again what the flavor is? I don't think I understood that right.
Okay, so the flavor is kind of, you can think of it of models. So here we're talking about CPUs, or this CPU is kind of the, it's kind of wrapping the entire VM. So in cloud you can have certain types of VMs, and then these VMs could be spot, could be preemptible, sorry, could be preemptible or not preemptible. Other example would be maybe I have ARM and Intel, right? And then I have different quotas for ARM, different quotas for Intel.
So the flavor is really the virtual machine flavor.
Correct. Yes.
Okay,
Yes.
not something related to the queue. I mean,
No.
it's
No.
related
No. No.
at the end, but okay, that's
It's
okay.
the flavor of the resource.
Okay.
Yes. And in the case of GPUs, you could have different models or maybe even different brands. So the idea is that your job has certain, so you don't have to define the node affinity for your job. Your job might be capable of running on different hardware, and then Q decides which one is the best hardware to use at the moment.
Okay.
And then all of the difference with, the default scheduler is that now it is guaranteed that all the pods that your job runs on are in the same model.
Okay.
I had a couple of, go ahead.
Was that a question? Sorry.
I had a couple of questions, but it sounded like maybe you weren't finished, Claudia.
No, that was it.
Okay. So my first question is about suspension. If a job is suspended, what is the effect of quota? Is it returned to the pool or not?
Yes. We haven't implemented preemption yet, but once, yeah, the idea is that once it's suspended, the quota comes back.
All right. And my other question is, what is the interaction of the cluster queues quota with the traditional resource quota? Say you have resource quota defined on a namespace, and you have adequate cluster queue quota, but maybe not enough resource quota in the namespace where it's scheduled.
Right. So the quota, since it works at the pod level, we wouldn't recommend using it because you could end up with partial jobs. So we would recommend that you only use the quota model from Q. Eventually, we would like to somehow make them work together, but that's gonna be very far in the roadmap.
And in
What-
general, like how would it interact with other types of admission controllers? I mean, does it evaluate whether or not it passes admission before scheduling?
No,
Or okay.
no.
I had
We-
another question.
we do some admissions, the most important ones, or like important webhooks, or not webhooks, but mutating admission controllers. We mimic the behavior, but not, we wouldn't support a custom admission controller.
I just want to add here that, like, for example, admission controller like Gatekeeper could be used to complement queue. For example, if you want to implement specific policies, who can use which queue, which cluster queue, for example, have something more advanced than what we have in built in queue, they would complement each other. And this is one of the design goals of queue, is not to re-implement existing functionality. Regarding resource quotas, resource quotas are going to be, like, usually it's used to protect the cluster from failing over, because they're not too flexible. Like, if they basically prevent you from creating the resource completely, and so you still need like a a control plane of your own to retry that when the quota is available. They're not going to retry it for you, right? Like, if you don't have quota to create pods, that's it, right? And if you continue to do that, like, for example, if you have a deployment and the deployment continues to try creating the pods, and the pods keep getting like blocked by resource quota, this is not a nice model, right? Like, you're gonna kill the control plane as well. Like so usually resource quota kicks in like at the limits, so you prevent and protect the cluster, not in a case where, oh, I have limited resources, I want to make sure that I maximize their usage, and so I have some sort of like queuing system that releases these resources and creates them at the right time. Does that like does that make sense? At least this is how we view how those like admission controllers, resource quota interact with what queue is doing, which is basically dynamic resource quota in a sense.
Yeah, that makes sense.
I think there was another question.
Yeah. Right. So I think I heard that you mentioned that the cluster queue selects the best flavor for running your job. Can you mention how does it select the best flavor to run my job?
Well, it's based on the existing usage. For now, we go the flavors in order. So if this is if you set this, you can always swap them, right? So we'll go in this order and try to use this. Now, you could think of different strategies. For example, you might want to prioritize not borrowing. Only use the flavors that you have available on your own. But yes, there's this kind of strategies we haven't implemented yet.
Okay, so this is still in works. I see. Thank you.
So I want to go through this. What do we ask from the ecosystem from Kubernetes? So from Kubernetes, what we are asking is that the job API advances to support more use cases. Of course, we ourselves have been working on a lot of these ones. We have, for example, failure policies, failure per index, or we are thinking about, like, should we add multiple pod templates in the job API or an alternative job? So this is the work that the working group itself is doing. And minor details, maybe add a queue name to the job API. Currently, it's hard to justify because queue is the only consumer and queue is not part of Kubernetes. So it's a little bit hard to justify at the moment. And then this is more of a longer request to add some kind of suspend of queuing or queuing subresource to the APIs, so that queue can suspend and unsuspend any arbitrary custom workload in an agnostic way. You might be familiar with subresources from, for example, the scale subresource. With the scale subresource, horizontal pod autoscaler can scale up or down any custom custom resource. And yeah, so the idea would be to have the same for suspending or queuing. And what do we ask to the ecosystem in general, like Kubeflow, Argo, etc.? So ideally, we would like everybody to use the job API. Not, we don't mean that you would get rid of your resource definitions, but you could still use a job as an underlying resource that deals with the pod creation. Of course, this is a very long-term ideal. So for the time being, we would like the ecosystem to also support suspend semantics and node affinity injection. So yeah, that's the idea. With that, I could go into a quick demo, live demo. Of course, that's gonna go well. Let me.
We have a question, Abhishek.
Sure.
Yeah, so I think I heard horizontal pod autoscaler, and I mean, frankly, I've been reading more about cluster autoscaler, and they react to pending pods. And so, if you decide to scale, then will queue react to pending pods?
Trying to cancel. So since queue doesn't queue would prevent the creation of pods, and once these pods are created, uh, everything starts doing what they are supposed to do. The kube scheduler would start scheduling the pods that are already fit in existing nodes, and once the pods that don't fit are marked as pending, the cluster autoscaler would kick in and create the nodes. So it basically everything is behaving the same way, except that queue is coming in the middle just to throttle the demands, and then so that workloads don't compete with each other for the resources when they don't need to.
I see.
So that in the future, we would like to have some more direct integration with autoscaler. That's also in the roadmap, so that queue can say, oh, I have all of these things pending. I can start already asking the cluster autoscaler to scale up. But that's still a long way.
Okay, so in the current model, you're basically working off pending pods, as I understand.
Yes, correct.
All right, thank you.
So with that, let me share my demo real quick. Can you see my terminal?
Yes.
Yes, we can.
Okay, I have too many. So here I have a system with two cluster queues. You can see them at the bottom. I have alpha and beta. They are running my workloads, and they are part. They are part of the same cohort. So the cohort all. So in theory, they should be able to share resources. Now the problem is that there are too many pending workloads in B, in beta, and once all these workloads complete, you will see that alpha will start borrowing resources from beta. Now, this is an auto-scale cluster. At the moment, well, it's maximum size because all of the resources are being used. Now for the given quota, right? So if I show so if I describe this cluster queue, you can see that, well, I have defined for the flavor on demand, I have a quota of 10 10 CPUs and 36 gigabytes of memory. So that's what we're seeing here. Well, 10 from alpha and 10 from beta. Okay, so now we are getting to the point here, down here in beta, where we no longer have pending workloads, but we still have pending workloads in alpha. So we can see that now alpha is starting to borrow resources from beta. Now all of the workloads from beta are running. Now, so I'm gonna exhaust the system, let's say. So now my everything. So both cluster queues are being overwhelmed. So I need more resources. So I have this extra cluster queue, which is currently in a different cohort. So I'm going to put it in the same cohort, and then this means that the other cluster queues can start borrowing resources. So now we can see that there are plenty. All of these workloads have been admitted. And let me just put this faster. This is just creating jobs. So let's give it a couple of minutes. This is an autoscale environment. So at the moment, the cluster autoscaler is working on setting these nodes up. So we should see them in a bit. But basically, that's the idea. Once the workloads are consumed, oh, there you go. So this is, yeah, the cluster autoscaler started. So now all of these pending workloads are being processed in these new nodes. And that's it. That's the demo. So you can see here in action different flavors and borrowing and fair sharing.
I just wanted to add here that part of the design for the API is trying to fill gaps related to queuing in a cloud environment. Like all these seemingly new concepts of like flavor, fallback, adding a new cluster queue on the fly, all of this usually doesn't happen in an on-prem cluster where you already beforehand, you know how much resources you have, it's fixed size. But in a cloud environment, like the example that Aldo showed that, oh, I have new cluster queue, it's not that like in an on-prem environment, it's not like you got a new shipment and, oh, I installed a new server. In the cloud, this can happen in an instant, right? Like you say, you decide, oh, I purchased this new reservation, or I decided to use more spot VMs because now they are cheap, so I can spend more money on them. And so you want all of that flexibility to be expressed in the API to use the power of the fungibility of the cloud and extensibility, right? So you can at any moment decide you scale up or down. And so you want to be able to express those. So hopefully you look at the API with that lens. It might look at the beginning as like a little bit confusing, or the concepts might not be too clear. But if you think of it in the context of the cloud, it might make more sense. Especially the example that Aldo gave, for example, on demand to Spot, etc., or various GPU models. It will make more sense when you start to think about it in the cloud environment.
And when you mean in the cloud environment, you also mean to be able to scale the cluster out and in.
Exactly.
Okay.
That's one thing. But the other thing is the various types of resources. Like in an on-prem cluster, you usually have one type, right? In the cloud, you have on demand, you have Spot. You have various machine families. Like in Google, you have C2s and A2s. Like you have multiple types of machines. You have memory optimized. Like all of these dimensions, you need to somehow be able to express how you want to use them, fall back between each other, and express different quotas for them. So usually you don't have that many dimensions on on-prem. On the cloud, you do.
Oh, by the way, that was a demo of version 0.1.1, and we're working on the release of 0.2. Hopefully, it should be out next week. We wanted to have it this week, but there's always a lot of cleanups here and there. So.
Okay, we have 2 minutes left. Are there any last questions for Aldo and Abdullah? Okay, hearing none. Thank you very much, all. Thank you very much, Aldo, Abdullah,
Thank you. Aldo.
and see you next time in 2 weeks. Bye, all.
Thank you.